A sigmatropic reaction in organic chemistry is a pericyclic reaction wherein the net result is one sigma bond is changed to another sigma bond in an uncatalyzed intramolecular process. The name sigmatropic is the result of a compounding of the long established sigma designation from single carbon-carbon bonds and the Greek word tropos, meaning turn. In this type of rearrangement reaction, a substituent moves from one part of a pi bonded system to another part in an intramolecular reaction with simultaneous rearrangement of the pi system. True sigmatropic reactions are usually uncatalyzed, although Lewis acid catalysis is possible. Sigmatropic reactions often have transition metal catalysts that form intermediates in analogues reaction. The most well known of the sigmatropic rearrangement are the 3,3 Cope rearrangement, Claisen rearrangement, Carroll rearrangement and Fischer-Indole synthesis. These reactions are particularly informative in that 1,3 hydrogen shifts are not observed. The reactant in the first equation is a deuterium labeled 135 cyclooctatriene. On heating, this compound equilibrates with 136 triene isomer and the two deuterium atoms are scrambled among the 4 locations noted. If 1,3 or 1,7 hydrogen shifts were taking place, the deuterium atoms would be distributed equally among all 8 carbon atoms. On prolonged heating or at higher temperatures, these cyclooctatrienes undergo electrocyclic ring opening to 1,357 octatetraene and reclosure to vinyl 1,3 cyclohexadiene. The second example shows another 1,5 hydrogen shift from the proximal methyl group to the carbonyl oxygen atom. The resulting dienol rapidly exchanges OH or OD before the 1,5 shift reverses. In this manner, the reactive methyl is soon converted to CD3. Since hydrogens alpha to a carbonyl group are known to undergo acid or base catalyzed exchange by way of enol intermediates, we might expect the alpha CH2 group to exchange as well. However, if care is taken to remove potential acid or base catalyst, the thermal 1,3 shift necessary for the exchange is found to be very slow. After learning this module, you shall be able to know what are sigmatropic rearrangements, learn nomenclature of sigmatropic rearrangements, identify rules governing feasibility and stereochemistry of sigmatropic rearrangements. Let us start by the introduction. Sigmatropic rearrangements, sigma designation from single carbon-carbon bonds and tropos from Greek language meaning turn, are a class of unimolecular pericyclic reactions. This class of reactions are characterized by the migration of a sigma bond adjacent to one or more pi systems to a new position in a molecule, with the pi systems becoming reorganized in the process. In the reaction, the total number of sigma or pi bonds does not change, as the reactant and the product have the same number of bonds. The sigma bond that migrates may be in the middle of the system or at the end of the system. These reactions are intramolecular in nature and generally do not require a catalyst for their completion. Following is an example of 3,3 sigmatropic shift. As you can see that the total number of pi and sigma bonds in both the reactant and the product are the same. Now let us talk about nomenclature and stereochemistry of sigmatropic reactions. Sigmatropic rearrangements are classified based on an order which is expressed by a set of 2 digits in brackets as I and j in square brackets. These numbers are determined by counting the atoms over which each end of the sigma bond has moved. Each of the original termini is given the number 1. For a sigmatropic shift, if the sum of I and j is an even number, it indicates the involvement of a neutral all carbon atom chain. If on the other hand the number I plus j is odd, it indicates involvement of a charged carbon atom or a heteroatom lone pair replacing the carbon to carbon double bond. When determining the order of a sigmatropic shift involving a hydrogen atom migration, it is important to count across all atoms of the chain involved in the reaction rather than only across the closest atoms. Following are the examples of some of the sigmatropic shift reactions. Sigmatropic rearrangements 1n are common for hydrogen atom shift with known examples of n equal to 2, 3, 4, 5, 6, 7 and even for longer chains. For these reactions, the feasibility of reactions due to stereochemical constraints is governed by the total number of pi electrons present in the substrate. If the total number of pi electrons is 4n plus 2, then suprafacial pathway is allowed, and if the total number of pi electrons is 4n, then anterafacial pathway is allowed. As you can see in the following examples, the first being an example of a 1,3 sigmatropic shift. The second reaction is a 1,5 sigmatropic shift. The third is an example of 1,7 sigmatropic shift. Anterafacial and suprafacial are terms that are described in Woodward-Hoffmann rules to describe relative orientations of molecular orbitals for bond formation. Woodward-Hoffmann rules are based on conservation of orbital symmetry. In a sigmatropic shift, if the hydrogen atom or migrating group leaves one surface of the conjugated system and arrives at the other end of the same surface, the reaction is said to be suprafacial. On the other hand, if the hydrogen atom or migrating group leaves one surface and arrives on the opposite surface, it is called anterafacial reaction. The 1,5 hydrogen shift involves a suprafacial reaction where the hydrogen leaves the upper surface at C1 and arrives at the upper surface at C5. We have the first reaction being 6 electron suprafacial 1,5 sigmatropic shift. The second reaction is an 8-electron antifacial 1,7 sigmatropic shift. This involves a 6-member cyclic transition state. In the transition state, the hydrogen atom is in contact with both ends of the chain at the same time. This calls for the molecule to adopt the cis-oid conformation as a must requirement. For the 1,7 shift with 8 electrons, antifacial pathway is taken up, in which the hydrogen atom leaves the upper surface of C1 and arrives on the lower surface at C7. To understand the stereochemistry of products formed as a result of sigmatropic rearrangements, Woodward-Hoffmann rules can be applied to various substrates under normal or photochemical reaction conditions. In the following diagram, some possible theoretical combinations are shown. Here, A stands for antifacial and S for suprafacial. R stands for retention and I for inversion. In practice, these rules can be summed up as follows. For supra, supra or antra, I plus j sigmatropic shifts. If I plus j is equal to 4n plus 2, they are thermally allowed, and if I plus j is equal to 4n, they are photochemically allowed. For supra-antra Ij sigmatropic shifts, if I plus j is equal to 4n, they are thermally allowed, and if I plus j is equal to 4n plus 2, they are photochemically allowed. Next, let us look at the reactions involving sigmatropic shifts. We start with the 1,2 shift category. Let us consider 1,2 shifts involving ionic conjugated systems. A number of named reactions follow such migrations. For example, in the reaction, if the migration terminus, migration origin and migrating groups all are the carbon atoms, then the reaction is known as a Wagner-Mirin rearrangement. If the migration terminus is a nitrogen atom, it may be a Curtius, Beckmann or Lawson rearrangement. When the migration terminus is oxygen atom, it is characteristic Baeyer-Villiger reaction. All these reactions are known to take place with retention of configuration in the migrating group. In contrast, 1,2 shifts in anions are rare as they are symmetry forbidden. In Stevens rearrangement, a 1,2 shift reaction occurs in an anionic substrate as shown. Next, let us talk about 1,3 shift reactions. Thermally, the antifacial shift of carbon is symmetrically allowed, with double bond acting as the antifacial component, but this does not happen because of difficulties of achieving effective orbital overlap. In practice, suprafacial shift of carbon occurs with inversion of configuration, where sigma bond takes up the role of antifacial component. This was not possible for hydrogen atom as it has only s orbital and lacks p orbitals. If we look at the orbital picture, it becomes clear that the newly formed bond is a little longer and thus should not be very plausible. As you can see in the diagram, nevertheless, the reaction has been shown to take place for suprafacial shift of silyl groups at 500 degrees Celsius with long silicon carbon bonds, making it feasible. Photochemically, a suprafacial shift with retention of configuration in the migrating group is allowed, and a number of such examples are known. A reversible 1,3 shift in verbenone, a plant-derived terpene, to give chrysanthemone is such an example of photochemical alkyl shift. The reaction is carried out at 20 degrees Celsius for a time duration of 1 hour. Another example of photochemically allowed 1,3 sigmatropic shift in steroids is shown. Next, let us talk about 1,5 shift reactions. As compared to 1,3 shifts, in the case of 1,5 shift, the suprafacial thermal rearrangements are quite common, while photochemical rearrangements are rarely observed. Following reaction gives an example of 1,5 shift, as can be seen in the equation. Antrafacial 1,5 hydride shifts are possible, although less commonly observed under photochemical irradiation. 1,5 migration of functional groups such as methyl and phenyl are thermally allowed, as can be seen in the given equation. Let us talk about walk rearrangements. In a bicyclic molecule, the migration of a divalent group such as oxygen, sulfur, nitrogen, alkyl or dialkyl carbon, which is part of a 3-member ring, is commonly referred to as a walk rearrangement. This is a 1n sigmatropic shift. An example of such a rearrangement is shown. The 1,5 shift in the walk rearrangement of norcaradines is expected to proceed suprafacially with a retention of stereochemistry. Next, let us talk about 1,7 shift reactions. Photochemical 1,7 shifts are suprafacial, and there are many examples of such reactions. As you can see in the equation, let us talk about a 3,3 shift now. These are synthetically useful, and there are several name reactions that fall under 3,3 sigmatropic shift category. The popularity of 3,3 sigmatropic rearrangements in organic synthesis is due to the ability of such reactions to generate stereogenic centers from the sp2 hybridized carbons. Claisen and Cope rearrangements are important name reactions of this class. However, they will be discussed in the next module. Following are a few examples of other most common 3,3 sigmatropic rearrangement reactions. Let us first start by the Fischer-Indole synthesis. It is a chemical reaction that involves synthesis of the aromatic heterocycle indole from a substituted phenylhydrazine and an aldehyde or ketone. This reaction takes place under acidic conditions. As you can see in the mechanism, a 3,3 shift is involved for the formation of the product, which is 2,3 dimethyl 1H Indole. Next, let us talk about Carroll rearrangement. This is a reaction that involves transformation of a beta keto allyl ester into an alpha allyl beta keto carboxylic acid. This substrate undergoes decarboxylation, giving gamma delta allyl ketone as the final product, as shown in the reaction. Next, let us look at the Ireland-Claisen rearrangement. This is an organic reaction of great utility as it creates two stereogenic centers with very high levels of specificity arising as the transition state involves a chair-like structure. Next, let us look at the Mislow-Evans rearrangement. It is a 2,3 type of sigmatropic rearrangement reaction that results in the formation of allylic alcohols from allylic sulfoxides. The reaction is useful for creating particular stereoisomers of the alcohol as it is highly diastereoselective and the chirality at the sulfur atom can be transmitted to the carbon next to the oxygen in the product through a sulfinate intermediate, which involves suprafacial shift of functionality, as you can see in the reaction. Next, let us consider 5,5 shift. Let us consider the 10 electron systems that include 5,5 sigmatropic shifts. As shown in the reaction, the 5,5 sigmatropic rearrangement of 2,4-pentadienyl phenyl ethers can be considered a homologous reaction to the Claisen rearrangement. As you can see from the mechanism, sigmatropic rearrangements are classified based on an order, which is expressed by a set of 2 digits in brackets, square brackets I and J. The shifts can be suprafacial or antrafacial depending upon the number of electrons and reaction conditions. The product's stereochemistry in case of sigmatropic reactions is anticipated using Woodward-Hoffmann rules. For supra-supra or antra-antra, IJ sigmatropic shifts, if I plus J is equal to 4N plus 2, they are thermally allowed, and if I plus J is equal to 4N, then they are photochemically allowed. For supra-antra IJ sigmatropic shifts, if I plus J is equal to 4N, they are thermally allowed, and if I plus J is equal to 4N plus 2, they are photochemically allowed. Some sigmatropic rearrangements involve polar components in the substrate. 3,3 sigmatropic shifts are involved in a number of name reactions such as Claisen rearrangement, Fischer-Indole synthesis and Carroll rearrangement.